So the next concept today we are going to learn about Adaline. Okay. So adaptive linear neural networks, and we have multiple adaptive linear model. Okay. So a network with a single, one second. Yeah. So a network with a single linear unit is called Adaline. That is, we'll have a single linear unit. Okay. And in Adaline, there will be only one output unit, and which are bipolar. So the either values are +1 or -1, and the weights between the input and output units are adjustable. And in order to adjust the weight, it will use the delta rule. So remember, what is an Adaline? Adaptive linear neural network. So it will use linear unit called Adaline, adaptive linear neural, and these output values will be +1 or -1. The weights are adjustable, and these weights can be adjusted only using the delta rule. Okay, so this is a basic information regarded to Adaline. Okay, so this is the weight adjustment formula. So how we are going to adjust over here? So new weight equal to old weight plus t minus y in of xy, where wy, y in, and t are the weight. Y in is the predicted output, and this is a true value respectively. Okay. So this is the delta rule which we are going to use for the adjustments of the weights. Okay. Why we are using the learning rule? So it is a mean squared error between the activation and target values. Whenever I'm talking about the target values, remember that it is a supervised learning method, and this can be trained in order to reduce this particular error between activation and target values. We will minimize this using the weight calculation. So we will calculate the trainable weights, and it will compare with the actual and calculated output based on the error training algorithm. So here we'll reduce the error by updating the weights. Yeah, so this is the diagram. If you see here, we'll have all the x1, x2, 4. This is the bias, and this is your net input function activation. And this particular error is passed to the back to this particular layer. And this error will be adjusted with the help of the weights. And this weight adjustment will be done with the help of delta rule. So remember these points. So first we'll calculate. So what exactly we are going to do here? So first we'll calculate the net input and apply the activation function as usual. Then compare with the original output. If both are equal, no issue. Then give the output. Else send error back to the network, which will update the weight according to the error, where error is calculated by the delta learning group. So this is the thing. So just I'm briefing. Step 1, calculate the net input, apply to the activation. If you're getting output and the output is equal to the original output is equal to the predicted or targeted, then fine. Otherwise, send the error back to the network. And this error can be reduced by updating the weights with the help of the delta learning rule. So this is the exact flow of the Adaline network. Adaline neural network. Yeah. So these are the values bias. Okay. All that in this one more point we have to remember. All these are connected to this particular directly to your y output. Okay. Previously we used to have the input values and directly we are connecting, but here this input will be directly connected to the output layer. We don't have any hidden layer. It consists of only single layer. Yeah, these are the steps. First, initialize weight, not zero, but small random values. You should not take any zero values. You can take some random values. Then we have to set the learning rate alpha. In order to do the condition, when to stop this, you have to do 3 to 7. So 3 to 7. For each training, we have to set the activation function, and you have to take the input, compute the input to output, compare with the threshold, and go for the error one. So step 3, what we are doing, for all 4 to 6. The 3 1, last 3, what is the last 3? Changing the range, comparing with your target output, and reducing the error. So step 5 is net input to the output unit. 1 second. Okay. Okay, first we'll discuss all the weights, then we'll go for the thing. First we read out the steps. So first we are going to initialize all the weight. Weight should not be 0, it should be some random value. And we'll set the learning rate. Stopping condition false. In order to check this, this have to be done 3 to 7. When we will stop the condition, when the threshold value is, activation value is, whatever the output we are getting is equal to the target, will stop. Otherwise, if you are going on changing the weights, then also there is no change, means we have to stop. So two conditions. One is when you get the same output with the target output. Second one, if you change, going on changing the weights also, there is no change in the result, you have to stop there. Okay. So next one, training purpose, we are going to the do from 4 to 6. So what is fourth step? We are calculating the activation of input with the xi equal to xi, comparing this one, computing the net input and output units. This is computing the net input and output, updating the, this is the delta rule. So Wi new equal to Wi old plus alpha is the learning rate, t minus y in of x sign. And BIOS also you are changing B new equal to B old plus t minus y in. And this is your error rate. So error equal to t minus y in whole square. So finally, we will get the predicted output is same, then weight will not change. Otherwise, you have to change this particular patch. So the stopping condition will be done when weight changes at a low rate or there is no change. So this is the thing what I told you. So we'll do one simple example. So initially all the weights are assumed say 0.1 and learning rate is 0.2 and least square error is 2. Okay. So according to this x1, x2, 1, 1, g. So these are the input values. All these are values. Now I'll calculate y in. What is y in? W1 in wi into xi plus b. So if I take here y in equal to 0.1, 0. Weight is 0.1 already we took into what is first one 1. Okay, into 1, 0.1 into 1 plus what is our bias? Bias also we took 0.1. See, W is 0.1, bias is 0.1. Okay. So what we are doing, okay, I can, yeah. So I'll do, I hope it is clear. So after calculating, I'll get 0.3. So t minus y in. Okay, y in was 0.3. What was t value? Least squared error was 2. Okay, t is also 1. So t minus 0.3 is 0.7. Now we have to calculate the new wage. So wa of new equal to w of old plus t minus y in into xi. So w1 of new. So what is wi? Old one is 0.1 plus what is our xi? Xi is 0.1. And what is our t? T is 1. What is y in? 0.3. So I'll get 0.17. Similarly, W2. And I'm changing the bias also, B new equal to B old plus T minus Y in. So B new equal to what was B old? 0.1. And what was our, okay, plus T minus Y in into, okay. So here it is 0.1 into, this is Xi. 1 minus 0.3, it is again 0.7. Now what is our error rate? T minus y in whole square. What was our t in? T value 1 minus y in whole square is 0.3. That is 0.7. 1 minus 0.3 is 1. 0.7 whole square is 0.49. Okay, like this we'll calculate for all the values. If you see here x1, x2, g, y in, t minus y in, delta w1, delta w2. This will be difference between first weight minus second weight. And delta b is the bias, difference between two bias. And this is w1 with the 0, 1. Okay, continuation is this one. Finally, I got the error rate as 0.49. Now, if you compute for the next one, so same values, you substitute for all the values. If you see here, it is changing continuously, it is increasing. So this error rate is increasing. So we'll do according, we can stop at the end where there is no change in the weight or there is no change in the error rate. So this is related, this is regarding Adaline. Now next one is multi-layered, multiple adaptive linear neuron. So it is a parallel with the single, consists of many Adaline in parallel. So what exactly Madaline is? Okay, I'll tell you. No. So if I'm taking one network, one is, this is one Adaline. Okay, I'm writing A. I'll take multiple adalines. Okay, one more A, and I'll take one more A. Okay, so these all combinedly is called as Madaline. So multiple adalines. So you can use multiple adaline models in order to complete the complete structure of Madaline. Okay, so it will have the single output unit, but you'll have multiple adalines. So the adaline layer is present between the input and Madaline layer, hence adaline layer is the hidden layer. So you'll have the input, in between you'll have the adaline, then you'll have the output layer. Okay, 1 second. Yeah, see, this is Madaline. I'll draw, yeah. So your input x1, x2 are inputs. So these two are okay, Z1 and Z2 are the adalines. This is your output. So now got it. So for bias, Z1, B1 is the bias, and Z2, B2 is the bias. And this is your X1. X1 with this particular weight is W11, with this particular is W12, X2, 21, 22. And again, these are connected to this particular networks. So this is a basic concept of Madaline. You can use any Madaline networks in the Adaline. So what are the layers? What are the layers? First, as I said, you'll have the input layer. Second hidden layer consists of Adaline layer. And third, you'll have the output layer. Okay, but weight can be adjusted only in between the input and output layer. That is 1 second. I'll show you where we can adjust the weights. So here we cannot adjust any weights, only in this particular, how many hidden layers are there. In these layers only, we can adjust the weights. In between, we cannot adjust the weights. So this is a basic rule of the Madaline. So the second layer will have the Adaline layers. Finally, we'll have the output layers where we'll get the final output. And these Adaline layers are all the hidden layers. So where we can adjust the weights. So for algorithm, the algorithm for is first we will initialize all the weight and learning rate as 0.5 and 0.5. It should not be 0. Stopping conditions as we see from the step 3 to 9 and training 4 to 8. So we are setting the activation for input as xi equal to si 1 to for I equal to 1 to n. Now we are computing the input of Adaline weight. So what we have done, bias plus x1 into w11, w12. So then we'll calculate both for 2. So if you have 2 neurons over here, we'll take those 2. Then we'll calculate this particular output with the Adaline using activation, because we have 2 Adaline layers, one is Z1 and one is Z2. So once I'm going here, so these are the 2. So these are the input values. These are the weights for this Z2 and Z1. So these two things, bias will be different, and these two values we will calculate over here. So with these two equations. Then finally, we'll calculate the net input for this Yin. That is Yin is again bias 3 here. So here we have the output with the B3. Then see, this is Z1 V1 plus Z2 V2, because from this particular Adaline, we have the weight value as V1. Here it is V2. So final summation will be Y, where it will be with the help of the bias B3. So then Y equal to F of Yin. So F of Yin is a threshold one. So if this particular threshold one is okay, I'm getting the targeted output, then no issues. Otherwise, I have to change the, yeah. See, if you get the output whose next is close to 0 or according to the threshold, no problem. If T equal to T is your target and Y is whatever I got, is no objection. Otherwise, I have to change with the help of this particular formula, which is of the delta rule. This is weight change and this is bias change. And if T is -1, then update on all unit ZK, we have positive net input. Then we have to go for the stopping conditions. Okay, so we'll see one simple example. So same thing, this is my training XOR function. So these are x1, x2 and t values. I have initial weights for alpha equal to 0.5. This is a learning rate. And these are the weight values, and these two are the bias, and this is V1 and V2. So this is according to the graph, and we have to substitute all the values in the given step. So in the first step, what we have done, x1 equal to 1, x2 equal to 1, t equal to -1, alpha equal to 0.5. Now Z in. So because we have two here, see this is Z1 and Z2. So this Z in 1 is calculated with the help of B1 plus X1 W11. So what is our B1? B1 is 0.3, X1 is value and W1 is 0.05. So X1 value is 1. So this your head 0, B1 is 0. What is our B1? 1 second. Yeah, so B1 it is 0.3 and 0.05 is W11 and X1 is 1 and W21 is 0.2 and X2 is 1 plus. So I'll get 0.55. Similarly, our B2 is 1 second. Our B2 is, where is B2? Yeah, B2 is 0.3. Yeah, okay. So B2 is 0.15. It is missing in the diagram actually. Here it will be B2. So B2 is 0.15 plus what is my X1? X1 is 1 and W12. If you see the diagram, W12. What is my W12? So this is W12 is 0.2. So from this particular value, it will be 0.2 into 1 plus 0.1 into 1. So I'll get 0.45. So I'll apply the function over here, activation function to get the net input. So I'll get f of 0.55. So what was the activation function here? This particular value. So I'll get 1 and f of this activation function is 1. And what is the computation output for this? B3 plus Z1 into V1 plus Z2 into V1. So what is my B3 value? 0.5. So B3 value is 0.5. 1 into, because here, 1 second. So V1 is 0.5 and V2 is 0.5. So V1 is 0.5 plus V2 is 0.5. So what is my Z1 1 and what is my Z2 1? So if I multiply all these values, I am getting this particular value. Again, f of 1.5 equal to 1. So because y is equal to 1, but my target value is -1. So these are not equal. So I have to update the weight. So what I'm doing, again, I'm updating the weights with the help of these formulas. So after updating the weight values, so W1 new equal to, I'll get this, after substituting the values, I'll get this 0.75, 0.625, 0.575, and updated weight will be like this. This will be only in the first step. Okay, so like this, if I continue for all the learning rates, I'll get the weight updation. Finally, I'll reach out the target value. So this is the Madaline and Adaline problems where we can resolve the complete supervised learning pattern. So you can explore more example, and thank you.